Welcome to today's paper reading. Today's paper is titled, RankRAG, Unifying Context Ranking with Retrieval-Augmented Generation in LLMs. This paper was published on the AR14 preprint by Yu and colleagues from Georgia Tech and NVIDIA. The authors introduce RankRAG, a novel instruction fine-tuning framework for large language models, LLMs. This framework is designed to enhance both context ranking and answer generation in Retrieval-Augmented Generation (RAG). By incorporating a small amount of ranking data into the training process, RankRAG-tuned LLMs demonstrate superior performance compared to existing expert ranking models, even those fine-tuned extensively on ranking data alone. In terms of generation, RankRAG models, such as Llama 3 RankRAG, significantly outperform strong baselines including GPT-4 and ChatQA 1.5 across multiple knowledge-intensive benchmarks. Notably, Llama 3 RankRAG also performs on par with GPT-4 on 5 RAG benchmarks in the biomedical domain without any specific biomedical data fine-tuning, showcasing its strong generalization capabilities to new domains. The paper introduces Retrieval-Augmented Generation (RAG), a technique used to customize large language models, LLMs, for handling long-tail knowledge, providing up-to-date information, and adapting to specific domains and tasks without modifying model weights. However, the current RAG pipeline has limitations, such as LLMs not being efficient at reading too many chunked contexts, which affects accuracy. To address these issues, the authors propose RankRAG, a framework that uses a single language model for both high-recall context extraction and high-quality content generation. RankRAG enhances the LLM's ability to filter out irrelevant context during retrieval and generation phases, improving the overall performance of RAG. The related work section discusses the application of Retrieval-Augmented Generation (RAG) in knowledge-intensive NLP tasks. RAG systems typically use dense embedding retrievers to fetch relevant information from external corpora, which is then utilized by large language models, LLMs, for text generation. Recent efforts have aimed to improve this pipeline by aligning retrievers more closely with the needs of LLMs, implementing multi-step retrieval processes, and filtering out irrelevant contexts. Additionally, there is ongoing research into optimizing retrievers alongside LLMs in an end-to-end manner, which presents challenges such as the need for surrogate loss functions and frequent reindexing of embedding databases. Ranking has been identified as an intermediate step to enhance retrieval quality, but current methods often rely on additional models that may not fully capture relevance or generalize well in zero-shot scenarios. Recent studies have shown promise in using LLMs for ranking tasks, though their application in the RAG pipeline remains an underexplored area. Figure 1 illustrates the performance of ChatQA 1.5, a robust RAG model, across different context sizes denoted by K. The figure highlights a critical trade-off. While a smaller K value may fail to capture all relevant information, thereby compromising recall, a larger K value risks introducing irrelevant or noisy context that can mislead the LLM's generation process. This balance is crucial for optimizing the effectiveness of Retrieval-Augmented Generation models. In Retrieval-Augmented Generation, a collection of documents or contexts is provided as grounded knowledge. The retriever, R, retrieves the top K most relevant context to a given question. The language model then generates the final answer. However, current RAG pipelines have limitations. The retrievers often have limited capacity, typically using sparse retrieval methods or moderate-size embedding models due to efficiency concerns. This limits their ability to accurately estimate relevance between the question and documents. Additionally, there is a trade-off in selecting the top K contexts. While increasing K can improve recall, it also introduces irrelevant content that can hinder the language model's ability to generate accurate answers. These limitations motivate the introduction of RankRAG, which aims to address these issues by improving retrieval relevance and enhancing both accuracy and efficiency. The RankRAG method is designed to enhance the Retrieval-Augmented Generation (RAG) capabilities of large language models, LLMs. This enhancement is achieved through a two-stage instruction tuning framework. In the first stage, supervised fine-tuning, SFT, The LLM is trained on a blend of high-quality instruction-following datasets, totaling 128,000 examples, ensuring no overlap with evaluation data. The training format is multi-turn conversational, focusing on the last response from the assistant. The second stage, Unified Instruction Tuning, builds on the SFT capabilities by incorporating context-rich QA data and retrieval-augmented QA data, aiming to optimize the LLM for both context ranking and answer generation, even with imperfect retrieval results. Figure 2 illustrates the two-stage instruction tuning framework for RankRAG. Stage I involves supervised fine-tuning, SFT, to enhance the LLM's instruction-following capabilities using a blend of high-quality datasets. Stage 2 focuses on unified instruction tuning for both retrieval-augmented generation and context ranking, ensuring the LLM can effectively use retrieved context for answer generation. This framework aims to optimize the LLM's performance on RAG tasks by addressing the limitations of initial retrieval results. Table 1 outlines the instruction template used in Stage 2 of the RankRAG framework. This template unifies various tasks into a standardized X-C-Y format, where X represents the question, C the context, and Y the answer. This format is applied to different types of tasks including context-rich QA, retrieval-augmented QA, context ranking, and retrieval-augmented ranking. By standardizing these tasks, the framework facilitates effective knowledge transfer and enhances the model's capability to handle diverse knowledge-intensive NLP tasks. In this section, we present the experimental setup, evaluation metrics, and main findings of our study. We conducted experiments on three types of tasks: open domain question answering, OpenQA, fact verification, and conversational question answering, CONVQA. We used datasets such as NQ, Trivia QA, PopQA, Hotpot QA, 2Wikim QA, Fever, Doc2Dial, Topiosi QA, and INSIT. For evaluation, we employed exact match, EM, accuracy, and F1 score depending on the task. Our main findings show that RankRAG outperforms existing retrieval-augmented generation, RAG, methods, especially on more challenging datasets. Additionally, RankRAG is data efficient and robust to the choice of retrievers. Table 2 presents the results of RankRAG and various baselines across 9 datasets, focusing on zero-shot evaluation. RankRAG demonstrates superior performance, consistently outperforming the ChatQA 1.58b model, which is a recent open-source model with state-of-the-art performance on many RAG benchmarks. Notably, RankRAG 8b is competitive even against models with significantly more parameters, such as InstructRetro and RADIT65b. With more parameters, RankRAG 70b not only outperforms ChatQA 1.570b but also significantly surpasses previous RAG baselines using InstructGPT as the underlying LLM. The improvements are particularly pronounced on more challenging datasets like long-tailed QA, PopQA, and multi-hop QA, 2Wikim QA, suggesting that context ranking effectively enhances performance in scenarios where retrieved documents are less relevant to the answer. Table 3 presents an ablation study of RankRAG using the Llama 3-8b model as the backbone. The table examines the impact of different components: retrieval-augmented QA, RQA, retrieval-augmented ranking, RAR, and the absence of re-ranking in the inference stage. It shows how the removal or inclusion of these components affects the performance across various tasks, highlighting the importance of context ranking and retrieval-augmented techniques in enhancing the model's effectiveness. Table 4 presents the zero-shot evaluation results using the Llama 2 model as the backbone. The data shows that Llama 2-70b achieves the highest performance across various tasks. Notably, RankRAG demonstrates consistent performance improvements across different model scales, with average performance gains of 7.8% for 7b, 6.4% for 13b, and 6.3% for 70b variants. This highlights the advantage of RankRAG in leveraging different types and sizes of large language models. Table 5 presents the performance of RankRAG on the Mirage benchmark, a zero-shot biomedical RAG benchmark. RankRAG, even without domain-specific fine-tuning, demonstrates superior performance in medical QA tasks, Notably, RankRAG 8B surpasses Metatron 70B, a leading open-source LLM for the medical domain, by 6.3%. Additionally, RankRAG 70B achieves over 98% of the performance of GPT-4. These results highlight RankRAG's ability to adapt to new domains without requiring additional post-training. Figure 3 compares the performance of RankRAG and ChatQA 1.5 using different dense retrievers on 3 representative tasks. The retrievers considered are DPR and Contriever MS Marco. Despite initial retrieval results not being optimal, RankRAG consistently outperforms ChatQA 1.5 by more than 10% on average for both retrievers. This demonstrates RankRAG's robustness to the choice of retrievers. Table 6 presents the ranking performance of various models, highlighting that RankRAG achieves superior performance compared to other models, even when using significantly fewer ranking data. Notably, RankRAG 70B attains 96.4% of the performance of GPT-4, a leading model, and maintains high recall rates across multiple tasks, demonstrating its effectiveness and efficiency in ranking tasks. Figure 4 illustrates the performance of RankRAG concerning the amount of ranking data used. It shows that RankRAG achieves better recall performance compared to other models, even when using significantly fewer ranking data. Specifically, with only 5,000 ranking data points, RankRAG can already obtain very compelling results. Further increasing the ranking data to 50,000 yields noticeable improvements, confirming RankRAG's data efficiency and adaptability across various tasks. Table 7 presents a case study comparing RankRAG 8B and ChatQA 1.5-8B on the NQ dataset. It highlights how RankRAG 8B, through re-ranking, is able to extract more evidence and find the correct answer, demonstrating its superior effectiveness. The table uses red text to denote distractors and green text to indicate evidences, providing a clear visual distinction between helpful and unhelpful information. In this study, the authors introduce RankRAG, a novel framework that instruction tunes a single large language model, LLM, for both ranking and answer generation tasks. The authors found that this instruction-tuned LLM can outperform existing expert ranking models by incorporating only a small amount of ranking data into the training mix. They compared RankRAG against state-of-the-art RAG models using comprehensive, knowledge-intensive benchmarks. The results show that RankRAG significantly outperforms all other models on 9 general domain and 5 biomedical benchmarks for RAG tasks. Thank you for watching.